long-term case study of developing a what kind of game in Unity?
Something RPG.
Some kind of RPG. It's either action RPG or turn-based RPG. We're not sure yet. We think we're going to hedge our bets and develop as much of it as we can and then do the combat system at the end. We'll probably figure out that the combat system won't actually be that much different between the two, but we'll answer that question in a few weeks. So we're going to start. Everyone has the latest version of Unity. If you go to help about Unity, you'll see that it says 5.4 point something. I have 5.4.0. Point 1 was released on Monday. You might have that too. If you have something really older than that, you should upgrade to 5.4 point something because we're going to be using some features in the engine that only just recently appeared. Okay? Okay. So assuming you have that, we go to our favorite view, 2x3, because we're going to use all these panels at the same time, especially scene and game view. We remember that from last semester, right? Sometimes we want to click on game objects to tweak them out, and sometimes we want to see what the game actually will look like in the game panel. To begin, we're going to make a new project so that we have a place to put our stuff. We're going to make sure it's 3D, and we're going to call it action or turn-based RPG. And we say create. And here we go. We've got a couple game objects already created by default. When you make a new project, you get a camera, you get a directional light. I think our old version of the engine used to do that too. For some people it didn't. I think for most people it did. So that's not unfamiliar. There's something a little bit new in 5.4. You're going to see that the name of the scene file currently loaded is up here in the hierarchy tab. There's a built-in scene file manager now that's new. And we're going to be exploiting that. If you don't see that, you're in the wrong version of the engine. But this also reminds us right away to save our scene. Save scene as. We're going to call it 1. And we've got a scene file asset right away in our assets folder. That's our first asset. When we start to look at developing multiple gameplay levels and when we start to look at separating global data in our game architecture from the gameplay data that changes stage to stage, we'll see that we'll have multiple scene files in our game. And we'll be pulling them in and out as we stream them or as we load and unload them. So managing our scene files will become important, probably in 2 to 3 weeks' time. So let's keep that in the back of our head. All right. So we're making an action or turn-based RPG. Our approach will be to develop some core gameplay for the basics of the game, and then we'll iterate on that and expand on that. Kind of take multiple passes at it to add more and more depth to it and develop more systems as we go. So if we're developing an RPG game, what's kind of like the part of the game where you're going to spend the most amount of time? What's the most important piece?
The world. Probably the world or the combat.
Definitely need a world. Who travels the world when you play an RPG? The main character, the avatar, right? So we'll start with that and the camera that looks at it. And this is actually a pretty common gameplay programming job. It's called the 3 C's, camera, character, and control. So we'll start with how we're going to move our dude in the world and what that looks like, and develop some code for that. If we're going to have a world, how can we approximate a world? What's the easiest way we can make a world to prototype some gameplay? We could do a terrain, but that's too hard because you have to paint weights and stuff. We remember that from last semester. We have to like import textures and things. We certainly could. Easier than that. Yeah, we need a floor. Let's do the floor the old school way. So there's our cube. We click on it, we can name it floor. We remember that. And we'll stretch it out to like, I don't know, 1,000 by 1,000 by directly inputting the scale in the scale field of the transform. That's our floor. And it kind of blends nicely with the default sky dome. So we've got blue and white there. We're probably not going to start with a snow level, so we're going to create some materials. Let's make our ground today. Make the color green. And then how do we make our floor green? Drag and drop. Cool. We're gonna use a simple piece of geometry to approximate our character controls to start. Make sure that kind of works and feels and looks good, and then we'll add a more detailed model on top of that when we start to make the character animate and stuff. What kind of, or what piece of geometry would make sense for prototyping gameplay of our main character? What would be like an easy piece of geometry to use?
Sphere.
We could use a sphere. Our guy's going to be a little bit taller than a sphere. Sphere would probably be easiest. I'm going to pick capsule. And it's, I see that I got my capsule here, but it's actually penetrating the ground, so I'm going to have to move that up. I'm going to type 1.5 into the Y component because I just know the default size of the capsule gets me touching the ground there. And I'm going to make sure that I can see my capsule. I'm going to make a red, and my guy is going to be red. So I'm going to drag red onto element 0. I'm going to make sure my red material is red. All right. How do I know which way my guy's facing? If my capsule is, or if my player is this capsule, where's his front? The blue arrow, right? Because we have this idea of Z forward in our Unity coordinates. So blue is forward, red is X to horizontal to the right, and yellow or green is straight up. And it's easy to see that in the scene view. When you click on a game object, you get its local coordinates widget, so you can know which way it's oriented. But when in the game view here, we don't have any way of telling what that orientation is. So we need to add an extra piece of geometry so we can see that. I'm going to do that by adding a hat to our capsule. It's just a cube. I'm going to make it a child. I'm going to put it up here so that it's, he's kind of wearing it on his head. I'm going to make it look long and narrow like that. All right. So this points the way, this points along the local Z axis, so I know that's the way my guy is facing. He kind of looks like a Dalek, if you watch Doctor Who, so that's cool. We like Doctor Who. There we go. Nice. Now if we rotate him around, his facing vector rotates, and we can see that in the game. The name of our character shouldn't be capsule. We want to make something a little more self-documenting. So I'm going to use hero this time. I might have used player before, or avatar. We're going to say the hero or the hero programmer or the hero system is what our main guy is going to be doing. Anything that's not the guy you're playing will be, you know, an NPC. All right. So there's our guy. What's next? I heard from the audience, let's make him move under user control. And that would be correct. So let's do that. If we're going to make our capsule, our hero, move under user control, what do we need? We need a script. We need a component that does that job because Unity is component driven. And when we start to talk about aspect-oriented programming and mix-ins and ways of designing our code to really take advantage of components, this is going to make a lot more sense. Why we choose to do it this way. We're going to call it hero control, hero CTRL. And how do we specialize the behavior of our hero game object so that it can take advantage of this script? I saw drag and drop and I heard drag and drop there, so we're going to do that. The alternative is also you can click add component and you can type the name of it until it auto completes. It'll highlight the one that matches the name and you can add it that way too. Of course, we don't want to have two copies of hero control, so let's just blow away one of those by selecting remove component right there. All right. So we want to edit this script. We want to make this interactive. We're going to double click on it. And your preferred text editor will open up. For me, that's MonoDevelop. For you, it may be Visual Studio or something else that you've selected in your preferences of your Unity. So here we are in Hero Control. We're going to leave ourselves a little comment at the top. We're going to delete that summary auto tagging here because reasons. We're just going to say this class is responsible for putting the hero under user control, i.e. joysticks, keyboard, etc. Okay. What's our approach going to be? If the hero is going to move every frame, because this is a real-time action game, even though the combat may or may not be real-time, we're going to need to update the position of the hero every frame. And to do that, we're going to need a special method to call in our update. So let's write that now. Hero control update. And we're going to call that from update. What's our general algorithm going to be in hero control update? We're going to get values from user input and then apply them to the hero in order to make the hero move. Sounds good, right? Nothing too new here. But to kind of visualize what we're doing when we grab the user input, we're going to add a public variable at the top so we can see what's going on. I'm going to add a public vector 3, and I'm going to call this inputs. And this will be, actually I'm going to call it axes. I'm going to call it inputs. I changed my mind. Okay? So axis values will be stored here so we can see them change in the inspector. Okay, I'm going to cache them and so put them in here so we can see what's going on as we click on the thing. That should make sense, right? Because we remember from last term, anything public, when we look in the inspector, we can see the values change. Let's do that. We're going to grab those values. So inputs.x, what would be a sensible axis or a sensible user input value to store in the x component here? Where do you think we're going with this?
Getting the player input from the keys.
We're actually going to not specify keys directly. We're going to use the input manager. Maybe it's going to come from the keys. Maybe it's going to come from the joystick. Maybe it's going to come from your Leap Motion or whatever device you have. But we want something to do with the x input. Horizontal, that's right. When we look in the input manager, we remember that we've got axes defined there. Horizontal and vertical come by default, but we may have others. How do we get the axis? It is get axis, but it's a method of a static class that the engine has for us. What static class implements get axis? It's input dot get axis. And we see, that's a good try. And autocomplete fills it in for us. Thank you very much, Unity. So it is a, returns a static float and it takes an axis name. So we need to use one of those axes and it is horizontal, in fact. If we need to add more, when we do the camera rotation, we'll add some more axes for the right stick, but we're going to use horizontal and vertical for the motion of the player. And similarly, for the vertical, we're going to store that in Z or Z because XZ is the ground plane and Y is vertical in our game engine. So we're going to keep that convention even when we look at user input. We're going to say get axis what? Vertical. Very good. If we go back to Unity and we click on our hero, we'll see that the hero controller script has now updated itself. We see inputs over here, and if we press play and set focus in the game panel, we should be able to see the X components go from -1 to 1 because I'm pushing my horizontal axis, and my Z is going to go from 1 to -1 there for up and down. So we're reading data nicely. So far so good? All right. Let's apply that to apply axis values to move the character. Let's apply that data to move our guy around in the scene. What are some approaches we could use to do that? You might remember from last semester when we were doing character animation, there were two ways of moving a character when it was an animated model. What were those two words?
Transform, translate.
Yes, we can use, in terms of code, transform.translate will move a game object. If you have an object that's playing an animation, there are two ways of actually making it translate around the world. Do you remember that? Blend tree is a way of combining two animations together. That's true, we did cover that. There's two ways of moving a game object that has animation. One is root motion, where you let the animation move the transform, and one is in place, where you manually move the object. Because we're not playing an animation on the object, we're going to use in place animation that will apply our character on top. And then we'll make a decision whether we want to use root motion or not. Okay? But because we're using this geometry to first start our character off, we're going to do in place, which means transform.translate, like you said. So, this dot game object dot, we'll just use transform. So our current transform.translate, this dot game object dot translate. Transform dot. There it is. There's 6 forms of translate, right? Each taking a different signature. One just takes a vector 3. What did you show me? Well, there we go. One lets us specify the coordinate system that vector 3 is in, either world space or local space. We've got these relative to. There's a version that takes just floats, and then the 3 variations on that. Let's assume we don't want to think about the coordinate system yet. We're going to translate it in a certain direction, right? What direction do we want to translate our character in when we push up on the joystick? Usually forward. Where's the forward vector on our game object? So what does that look like? Vector 3.z? I don't have that. Definitely right. We're going to take the inputs dot z value, so that's either going to be 0 when we're not moving forward or 1 when we're pressing full forward, and we're going to multiply that by a certain vector in order to translate it. So we're either going to not translate it when the inputs is 0, or we're going to fully translate it when the inputs is 1. But what's the vector we're going to translate this thing by? This dot transform dot forward. So there's the forward vector out of our current transform. No matter which way we're facing, it's either going to be this way, this way, this way. No matter which way we rotated it, we're going to scale that by z. And our thing should move forward. Let's try it. We press play. We're going to zoom out a little bit in the scene view so that we can get a good sense of what's happening. There we go. And if we set focus in the game, I'm pushing forward to go forward, I'm pushing back to go back. Not bad, right? That seems to make sense. How can we know if our game's actually working correctly? Let's test it by rotating our guy 45 degrees. Push forward, push back. Is it correct? Maybe we need to look on top. Is he walking straight? I'm pushing just forward. I'm pushing just back. Not really. Let's test it even further. Let's rotate it 90 degrees. Okay, now we push forward and back.
No.
Is he walking forward and back?
Yes.
Technically, but is he walking
He's not walking
to the direction of his facing?
No.
No, he's not. Why is that?
Because the direction we put it, basically a hard code to that direction.
There is a problem. Unity 3D transform.translate. It's already in my search history. And it's already clicked. Let's just go back there. Okay. Moves the transform in the direction and distance of translation. If relative to is left out, pay close attention, or set to space.self, the movement is applied relative to the transform's local axes. So we've left the relative to out. So the vector that we're translating our character to is relative to its local axes. Now, by taking this dot transform dot forward, is this dot transform dot forward changing when we rotate our character?
No.
Let's check. Because it seems like the more we rotate it, the more off from correct the translation is, right? And we're translating it relative to its local coordinates. And its local coordinates are always z is forward, right? 0, 0, 1. The z vector is forward. So to test this, let's go back into the engine and let's say forward. Let's call it v forward. Okay? And let's say v forward is equal to inputs.z. Actually, let's not even scale it. Let's just say this.transform.forward. And when we translate our guy, we're going to move it by v forward. Capital V. I don't like capital V there. I want lowercase v there. I want lowercase v here. Okay? And let's see what's happening. Okay? Because at least we can now see the numbers in the editor. Going back in here. So relative to our local coordinates, we're moving at a x of 0.01 and a z of 1. That's basically 0, 0, 1, right? Because the angle is just a little bit off. If I set that to 0, he's going to be, now he's rotating directly along his forward vector, 0, 0, 1, right? Because here's the forward vector, v forward, 0, 0, 1. If we rotate it 90 degrees, what are we saying here? We're saying we're going to translate our guy relative to its local coordinates at 1, 0, minus 1. Is 1, 0, minus 1 the same as his forward? No, it's actually off by 90 degrees. So actually, with this implementation, the more we rotate our guy, the more his translation is going to be off. What we need to do is say, instead of translating by the forward vector, we need to translate in his local coordinates. We already gave the answer. The direction we want to translate him is always, no matter which way the character is facing. Forward, if I'm only looking in my own coordinates, forward is always what vector? Z, 0, 0, 1. So that's vector 3 dot forward. Always 0, 0, 1 relative to our local coords. No matter what way we're facing, we always want to go forward. Do you think, does that look like we're moving forward? Agreed? All right, let's test it. Try 45. Are we moving forward?
Yep.
Yes, we are. Let's try 90. Are we moving forward?
Yep.
Yes, we are. Let's try 180. I think we're on the right track here. Whoopsie daisy. 180. That's forward, that's back.
Yes.
All right. So good. The point here was just to remind ourselves, because we saw this last semester, coordinate systems matter. If we're translating in local coordinates, the direction we want to translate is 0, 0, 1. If we're translating in world coordinates, the direction we want to translate is this dot transform dot forward. Because this dot transform dot forward is actually rotating when we rotate our guy. Forward isn't. And because the default is local, that means we're going to use 0, 0, 1. And so that's why this works.